about the first technology assignment, which is the technology assignment is related to a piece of software called GeoGebra. It's available online. It's completely free. It's one of those things that it's kind of like if you've ever heard of Desmos, or well, GeoGebra is like Desmos, but there's also other open source sorts of online resources out there beyond just textbooks, because what a lot of people have been doing is they've been writing textbooks and then just making it available to the public. And they just kind of count on the goodwill of others. So donations and things like that, grants from the government, fellowships and stuff like that. All right. GeoGebra and Desmos are along those lines. So basically the day that it becomes not free is the day that they'll stop upgrading it. It'll just be a platform that's available online. Same thing with Desmos. It's free because they're getting funded by grants, fellowships, and things like that. If the money stopped coming in, then they wouldn't have the means to continue developing it. So it would just stop. Not as in it wouldn't exist anymore. They would just stop advancing it. Like whatever the functionality is at that moment, that would be the functionality for the rest of the time. All right? Right now, it's pretty powerful to begin with, so I'm going to show you how to use that, because in the last unit, we spent a lot of time making graphs by hand and been playing around with those graphs on the calculator. But I mean, you know, you're sitting in a business meeting of some kind and you're displaying a graph to somebody, or you're trying to prove a point to somebody graphically or using statistics. I don't think you're going to be whipping out the old TI-84 to do that. All right, odds are you're going to be using some more advanced technology like Excel or Google Sheets or something along those lines. So we want to learn some of those. I keep it free. I always keep it free. We're gonna learn about some of those online resources. All right. So with that in mind, instead of working with Excel, we'll work with Google Sheets for the second technology assignment, because that's the free one. Excel, yeah, you could get it through a school account. But if you move on from here, you're not a student anymore. Unless you have it through the workplace or something like that, you're not going to get it necessarily for the discounted rate or even for free. All right, so that's a little bit of the lay of the land. I don't anticipate staying the full time today because you can kind of hear where I'm at. Again, I don't know how it happens. I mean, I know how it happens. Vitamin C is a thought that passes fleetingly through my mind. It just never actually ends up being part of my daily regimen. So that's the reality of it. All right. And I discovered, because it existed for a while, I just didn't know about it, and I'm supposed to be the one who's like really cool with technology. Apparently PowerPoint has a screen record function. I had no idea. So while I'm sitting here like a schmo for like 45 minutes after class trying to get that other software to save the video, this does it instantaneously. Yeah, you learn something new. Sometimes, I mean, I'm generally the kind of person that needs to learn new things the hard way, so I had to do it. All right, so probability. I think I kind of covered that, but I'll go into it again. These little... In case you're wondering, these little jammies up here, these are the pages in the OpenStax textbook. Sorry, not pages, sections. All right, because probability, more so than in the last unit, kind of falls into the category of, if you don't get it the first time, you can seek out other resources and practice a little bit more and you'll get it, all right? Because sometimes it's like, oh, I see how you did it there, but now I don't have anything to try on my own because I just did all the problems that you did in class. How do I know I really got it? The OpenStax textbook could be the place to go, all right? The link for that is in the syllabus. It's all on my website. All right, I'll point that out later when I take you through the tech assignment if you've kind of lost track of that. All right, so probability is a branch of math that deals with the chance of an event occurring. right? So that's as simple as that. What are the chances that it's going to rain? And I look at probability as a way of making decisions about daily life, games of chance, things like that. But really, it's more a number designed for you to do with what you will, right? Because, like in a vacuum, solve for X. What does it mean? Like what do we get for it or from it? It doesn't really tell us much of anything. But if you're using it to make decisions, that's where it develops its importance. All right. So every morning, I ask Alexa, "What's the weather today?" And she tells me, and then I make a decision. Like we all go through our routines differently. Some of us do it the hard way. You get dressed, you walk out the door, and then you're like, "Oh, it is much colder than I anticipated." And then you go back inside and change your entire outfit, and then you're ready to go. Right? Some people put on News 12. Some people go to the internet. But you're collecting information to make a decision. All right. If you're looking a couple weeks out, I know people who plan out their outfits for weeks in advance. I have a colleague at the high school. She hasn't said it, but I know for a fact that she has. There's no way she doesn't do this. Like her outfits are planned because they're color coordinated in every possible way. There's no way she does it on the fly in the morning. So, but she can't do that in the morning without knowing what the conditions are outside. So the forecast comes into play. All right. So these are some things that happen. And so what is a forecast? A forecast is giving you the probability of the weather being in a certain state at a given time. All right. They can usually with a reasonable degree of accuracy, 5 days out, give you a good sense of what the weather is. 10 days out, it's a little eh. So, it's definitely not an exact science, but it'll kind of get you in the right neighborhood. Now, if you're in a season where it's typically snowy, you wouldn't expect it to be sunny skies and 70 degrees, but that has happened too. So the forecast could give you a sense of that, but that's all probability. All right. An event is a collection of the outcomes of a procedure. I would even suggest that this is, in a classroom, these are really more desired outcomes. In real life, not necessarily the case, because we will have to kind of bridge the gap between what happens in a math class for probability and what happens in the real world. Because generally, you know what you want in a class because the question tells you what you want. Find the probability of this, find the probability of that. But in the real world, oftentimes it's investigation. Like, I don't know what's going to happen. Let me find the probabilities of a bunch of different situations and see which one is more likely to occur. All right. You kind of go in with a blank slate without really having any kind of sense of what's going on. A sample space is a complete list of all possible outcomes of an experiment or activity. All right. So every possible outcome. Now, it's going to seem kind of weird when we work on word problems in this unit to think that something is actually an experiment. It's like, wow, you're taking liberties with that word. Activity, you'll give me. You'll say, okay, I'll give you that's an activity. But an experiment, come on, man. This isn't a science class. If I flip a coin and roll a die, is that really an experiment? Well, I would say that at one point it was, because before we knew everything there was to know about coins and dice, there wasn't an experimental component to it. But now it's like it's an old hat. There's two sides to a coin. You want the probability of getting heads? You want the chances of getting heads? Well, there's one of those. There's two sides. It's more in the common sense variety. But if I wanted to figure out what's the probability of getting 5 heads in 10 tosses of a coin, like that, it's not guaranteed to be a 1 and 2 situation, right? So it may seem like it is, but we're going to learn some techniques down the line that prove that it won't be. All right, so that makes it kind of a little bit of a different situation. But what happens is you don't necessarily have a formula for that. If you don't have a formula for that, then sometimes you do have to experiment to figure out what the probabilities are, right? But that's not really why I bring this up. The reality is you're not going to walk out of this classroom and think to yourself, all right, I'm going to talk to a counselor down in the student center. I'm going to talk to someone, a career coach or something like that. I want to get into the coin flipping business. I want to see what that's all about. I bet there's a lot of money in there. Oh boy, that was bad. I should just stick with normal jokes instead of the corny, cheesy ones. So anyway, yeah, that's not what's going to happen. What you're going to do is use what you learn about probability and statistics from these elementary cases in order to actually tackle some real life situations. Because an experiment, you're talking like, medical sciences, engineering, you're talking, weather forecasting and things like that. Like you can experiment in a lot of different ways, and it has nothing to do with coins and dice and a deck of cards. So, but we learn it in this context because then, it's a simpler case, all right? So then we can apply it in a much easier fashion, all right? So the notation, we always love notation. Some of it's obvious, some of it's not so much. P is for probability, until it's not, unfortunately, because in the next unit, P is going to stand for a proportion. But fun fact, proportion is another name for probability. So why call it a proportion? Whoever created that topic decided they wanted to call it a proportion, and nobody argued with them. Right? So that's the issue there. A, B, and C, basically anything in the beginning of the alphabet denotes specific events, but there's nothing wrong with you actually using the name of whatever the event is. So, for example, where it says P of A, the probability of event A occurring, that's function notation from college algebra. So this is P of A. You could say something more specific like probability of tails when you're flipping a coin. That would be P of tails. And the P again is probability. So probability of getting a tails when you flip a coin. All right. So there's no reason why you have to create let statements and use it to denote this particular situation. Like let A equal tails and then write P of A all the time. Unless you're going to write P of A like 13 different times, then you may want to do that because it's less writing. Right? But all this is saying, notation-wise, is that it's the probability of an event occurring. So, and the reason why I'm harping on this is because people have looked at that in the past and they say, I get everything about this unit, I don't understand where the P times A is coming from. All right? It's notation. It's kind of like, think of it as f of x. So this one is like f of x from college algebra, or even, well, it could have been college algebra functions and models, college algebra trig, a variety of different courses. Now, the little tilde in front of the A means not, so I think that's pretty straightforward. But there's another term for it, because of course there is. Why wouldn't there be? Honestly, I think the terminology is the only thing that makes probability and statistics challenging. Also, we could say the probability of A with a little c after it, which is the complement of event A. All right, but what we gain from that is actually something fairly simple. It just means that the word complement means generally the same thing as a not, or the opposite. All right, it means everything else. So if I'm talking about the probability that it's going to rain, then the complement of that would be the probability that it's not going to rain. Right? But unfortunately, it seems that it's just another thing to know. Right? All this other stuff here in the experimentation, formulaic approach, and estimation pattern recognition, I've actually already discussed that. So I can kind of go through it a little bit quicker. Experimentation is when you have no idea what the probability is, so you're going in with a blank slate. So I don't know what the probability of getting heads is, so I'll flip a coin a bunch of times and see what it's trending towards. Right? So if I flip a coin twice, for example, I could walk out thinking that the probability of getting heads is 2 out of 2, which is not true. Right? Because on one side of the coin is the heads and the other side is tails. The probability should be 1 out of 2. Right? If I flip the coin 10,000 times, 100,000 times, 1,000,000 times, whatever, I'm going to get closer and closer to the true probability. That's what the law of large numbers states. Right? It tells us that as we increase the number of trials, the true probability is going to start to reveal itself. Right? Because for small samples, it is possible that you could get some extreme results. All right? So, I mean, you just look at it and say, you just kind of equate it to people. I mean, I could walk into my classroom on any given weeknight and think that 90% of the population is vaping. All right? Because if all I'm doing is just observing the people that are just whipping out their vape pens and just going nuts with it, I'm like, well, I just saw 10 people, 9 of them were vaping. All right, 90% of the population vapes. Is that a reasonable? No, I can't say that. It's not. First of all, it's not a representative sample. It doesn't represent the entire population, and I'm not even talking about like races, religions, and stuff like that. I'm talking about the fact that these are the people that I'm encountering between my car and my classroom. Right? So, like, it's so limited in geography to discount any possibility that it could be representative. Right? But the sample size is the most important thing. Right? So if I only encounter 2 people and they're both vaping and I say, well, 100% of the population vapes, that's not fair. Right? So, and you see that all the time. People kind of making policy based off of the behaviors of the few. And you know, one of my colleagues calls it the TSA rules. Like, there's a reason why we have to take off our shoes at the airport. You know, like it's the few that dictate the outcomes for the many, but that's a more extreme circumstance, because in those cases, you know, like the behaviors of a few are so extreme so as to impact the many. So in that case, you could actually look at the few as being maybe more impactful than a large group, because they are impacting a large group, you know, so 1 equates to 300 or something like that. Right? So, you know, it's tricky, but the idea is that as you increase your exposure to the entire population, you're going to get a truer sense of what really is going on. Right? Because, and you just think about it with different cultures. You know, like if you were to decide that teenagers in Westchester County are all anti-Semitic because you watched the news on, what was it, last Wednesday? Yeah, I watched the news from noon to 1 o'clock. And you saw that there was vandalism in a bunch of different places, religious places, Jewish synagogues and memorials and things like that. Yeah, so now you're going to draw a conclusion about an entire population based on those few instances. Definitely not fair, but you could see how this concept ties together to the real world in a more meaningful way. Right? So some extreme examples, I'll admit that, some uncomfortable examples, but that's the whole point. Because what we want to do is we want to move away eventually from the coins, the dice, the cards to, all right, Now let's see what we learned about that stuff. Can we apply it to the real world? Because the real world is a messed up place. Let's see if we can use probability to kind of try to make some sense of it. All right. So with that being said, the formulaic approach, how often is that going to work in the real world? Not often. I mean, what's the formula for determining the probability that somebody is going to do something terrible or do something wonderful? That's not how it works. It's all data analysis, right? So the experimentation and estimation pattern recognition. But in this course, we learn about the formulaic approach for a couple of reasons. One, because if something actually does fall into one of those categories, we can tackle it. Specifically the either or situations and the and situations. So multiple events involve multiplication, and either or events involve addition. So just simple probabilities, simple operations. The other more practical way of looking at it is, I got to test it on something. So formulaic approach. It's easier to put together some problems on a test or stuff like this. So that's the other thing. Basic probability rules. So basic probability rules, and this is the most basic. The coefficient of determination from the last unit, when we were talking about correlation, regression, linear regression, line of best fit, it kind of flows along the same, or flows the same way as basic probability rules. That 0 means, in this case, impossible, and 1 means it must happen. So before it meant that 0 meant that there was no relationship, and 1 meant that there was a perfect relationship. All right, so it still has the same general structure. So if you look at these in terms of percentages, I think it makes more sense. But we're going to work with them as decimals. So this is the same as 0%. And this one is the same as 100%. All right. The difference between the two is pretty straightforward, I think. All of something, none of something. But the meaning of them can be a little iffy. The 0 and the 1, they represent impossible and must happen, not through an experimentation, but because that's the nature of the experiment. All right. So if I were to say, here's a bag of marbles. Oh, marbles is another thing. We like marbles in this class too. So dice, coins, marbles, and then when you have an opportunity to do some research on your own, that's when you're going to be able to take your own personal interests, which I'm excited to see, and tie these together, because it's really cool. That's I think where people get the most meaning out of this class. I'll talk more about that down the line. If I have a bag that's got red marbles and green marbles in it, and I say, what's the probability of getting a black marble? Well, it can't happen, right? There's only red and green, so that's a 0. Now, if I say, what's the probability of getting a marble? That doesn't matter what marble it is. I'm always going to get it. I'm always going to have success. All right? So that's a 1. Now, if I say, what's the probability of getting 3 red marbles? And so what you do is you reach into the bag. You pull out 3 marbles. And, oh, look at that. It turns out that they're all red. 1. Probability of 1. No, probability of 3 out of 3. Okay? So probability of 3 red marbles from a bag, a bag containing red and green. And for this example, it really doesn't matter how many of each there are. It turned out you got 3 out of 3. We would not write that that's equal to 1. All right? That's probably the weirdest aspect of probability. You're not going to write that that's equal to 1. Now, 3 divided by 3 is equal to 1. But this is what you would report as your final answer. Because a 1 means that it must happen. It's not guaranteed that you're going to get red marbles every single time, or 3 red marbles every single time you do this. All right, you're going to get, there's going to be a set of trials that you conduct in which you're going to get green marbles only, or a mixture of red and green marbles. All right, but this one case gave you all greens, so that's possible. You know, maybe you just got lucky. All right, but it does not equal 1. All right, you flip a coin 5 times, and you got heads all 5 times. That's 5 out of 5. That's not equal to 1. All right, it's a subtle difference between the two. I'm not in the business with probability of asking trick questions on tests. So if you're one of those people that kind of squirms in your seat when you're like, it's going to be on a test and I'm going to get it wrong because I'm not going to remember that because 3 divided by 3 is equal to 1 every other day of the week except for apparently Saturday mornings. I'm totally going to screw this up. I'm not going to ask you a question like that, a trick question like that on the test. All right, it's really more for instructional purposes. All right, I figure that probability is quirky enough as it is that I don't have to go out of my way to try to trick you. All right. So the complement rule tells us that if we add 2 opposite events, that the result should be equal to 1. That's the must-happen one. All right, and so the example here, given a multiple choice question with 5 choices, what's the probability of getting the correct answer by guessing? We've all been down this road before. So probability of getting it correct just by guessing. Now, ideally, you don't go into a multiple choice test and guess on every question. But every now and then you come across a question and you're like, this one's a doozy. I really just don't know the answer to it. So you take a stab at it. You got 5 choices. One of them's correct. So you got a 1 in 5 chance of getting it right. That's all there is to it. Right? Like I said, simple probabilities to start. Now, the probability that you're going to get it incorrect, and this is why we study, that not symbol, again, that's the tilde. Now, I've had people use the letter like a funky script N to do that. I don't really care. Like, the notation, as long as it's somewhere in the neighborhood of the correct notation, that's fine. In fact, I mean, you've seen my handwriting, so like obviously I'm willing to let a lot of things slide. So you have 1 that's correct, so 4 of them will be incorrect. So obviously it's not a situation where you want to have to guess on too many different questions because it's not going to end well. But they're asking us to verify the complement rule. Verifying the complement rule is just as simple as saying that these 2 probabilities, probability of C plus the probability of not C, poor quality not symbol, should be equal to 1. All right? So 1 out of 5 plus 4 out of 5 is equal to 5 out of 5. But in this case, we are accounting for every possible outcome. So that result will be equal to 1, so this checks out. So I put a little check mark. That is an attempt at a 4 over 5, yeah. My handwriting's not good, but it's not as bad as this app is making it seem. Because like I'll write an entire sentence and it'll just put like little dots there and give me nothing. And I'm pushing down hard. And I even got this stupid glove. Like half my hand is sweating. I'm like half of a thriller. Breaking out the old jokes. So, anyway, basics. The basics of probability. We have rounding rules, and my point behind these rounding rules, to some extent, is to kind of talk you into just putting your answer in fraction form. Because I know people can kind of shy away from fractions. They want to use decimals, but decimals are a pain. Like, maybe you're like, well, fractions are a pain, and I say, well, agree to disagree. I don't know. Some solutions that you get are going to be so disgusting in decimal form that you're going to have no choice but to round it. But then once you convert it over to fraction form, it's like, oh, it's actually not that bad in fraction form, so I'll just go with that. So if that's the case, why not just put it in fraction form? Besides, if you put it in decimal form and round it, you're losing some accuracy. Fraction forms will be the most accurate form. All right, so I'll talk to you about how you can work in fraction form and stay in fraction form. And if you get an answer in decimal form, how to tackle it in a little bit. But the rounding instructions are 3 significant digits. There's not sig figs, not like chem. It's basically saying the first 3 non-zero values after the decimal point, that's where you start your rounding. All right, so I'm going to start my rounding here after the zeros end. And so 721 is what I'm going to end up with. Now, there were no zeros after the decimal point to start for the first one, so I could just round that straight away. There was no problem there. So you may have heard of the term odds. Odds for something or odds against something. So this usually happens in games of chance. But it's kind of weird because when you're talking about like a casino game, they usually give you 2 types of values, 2 types of numerical values. One would be the probability of winning, and then the other would be the payoff odds. Right? So you're not actually going to see the odds part of it too much in a casino game, but that's okay because what we're part of the unit is actually us exploring some casino games. So, like, I don't anticipate that everybody's going to be able to leave directly from class and go down to Atlantic City and clean up, but you should have a better sense of how to go about things when you're in a casino. So, like a little public service for you. So the odds for an event occurring is the probability of the event happening divided by the probability of it not happening. So it's as simple as that. So if I want to have the odds to roll a 4, all I'm going to do is find the probability that I'm going to roll a 4 and divide it by the probability I'm not going to roll a 4. All right, so probability of rolling a 4 is 1 out of 6. They gave that to us. But even if they didn't, it's when they talk about a die, they're talking about a 6-sided number cube. And that 6-sided number cube has the numbers 1, 2, 3, 4, 5, 6. I kind of spell it out a little bit more on the next page. All right, so those are attempts at squiggly brackets around the 1 through 6. But that 6-sided number cube contains the values 1, 2, 3, 4, 5, or 6. They don't actually have the numbers written on them. They just have dots corresponding with those numbers. But I always do a little intro on that because more and more as the years go on, there's less and less people that are familiar with that as the term for something that they probably already know. Like when you play the game of Monopoly, you pull out the game pieces and you just start playing. Over the years, I've discovered that there's actually been a pretty solid segment of the population of all different varieties that just didn't know that it was called a die. All right, so I figured I'd give you that. All right, so the probability that you won't roll a 4 would be everything except for the 4. So we have 1, 2, 3, 4, 5, and 6. One of those outcomes is the 4. I want everything else. So everything else would be the other 5 values. So 5 out of 6. All right, now when you simplify, this becomes 1 over 5. All right, because the denominators in a complex fraction, if they're the same, they cancel out. It's like the first time we've used an algebraic concept in this course. It's almost the middle of October. It's crazy. I mean, we didn't even do it algebraically. We did it numerically. But it's the idea of, like, if you have a fraction over a fraction, what happens? If the denominators are the same, you can wipe them out. Okay? So this is the same. This 1 over 5 is the same. So it means 1 to 5. Or you could write it in colon form, 1 to 5. All right, so really all it's doing is spelling out the number of ways in which you could win compared to the number of ways in which you could lose. All right, so 1 way to win versus 5 ways to lose. It's the same thing with the dice, not the dice, the multiple choice question on the previous page, except it wouldn't be 1 to 5 in that case. It would be 1 to 4, because in that problem you had one way to win, 1 way to get it right, 4 ways to lose or get it wrong. Right, so you'd have a 1 to 4. This is the basis behind how they make a determination of what the payout would be in a game of chance. All right, so if I'm creating a game related to just simply rolling a die, well, I'd have to balance these probabilities. So if I were to tell a person, okay, I'm going to bet you $10. You lose $10 if you get anything other than a 4. But I'll give you $10 if you get the 4. They're not going to play. All right? Their chances of winning are not reasonable. All right? But if I tell them, all right, you roll the die. If you get the 4, I'll give you $50. But if you get anything other than the 4, you gotta give me $10. All right? Now it's a fair game, because even though in one trial the person orchestrating the game could end up giving up $50, in the long run, they're going to break even, right? Because if you play, consider it's a small sample, but conceivably, if you play the game 5 times, a person could lose 5 times, so they have $50, right? The orchestrator of the game. And then on the 6th roll of the die, maybe somebody hits the number 4, and then they have to give the $50 back. It's a break-even approach. All right, but what happens is casino games, they orchestrate it so that it's ever so slightly in the favor of the house. So it's not noticeably an unfair game from your perspective, but over time, with millions of people coming through the casino and now doing it online, they make a ton of money, because instead of it being a perfect zero balance, they'll have it just a couple of cents in their favor. And so it's kind of like if it's only a couple of cents in the favor of the house for each individual person, they're like, oh, well, I'll play the game. It'll be fun. It's not a completely unfair game. But then the house looks at it as like, well, 2 cents from you, 2 cents from you, 2 cents from you, 2 cents from you, and then like millions upon millions of people over time, and before you know it, they have a thriving industry, right? All based off of this stuff. So I always make sure I put this disclaimer in there. Not a disclaimer on my end, but like if I'm going to talk about games of chance and gambling, I am always aware that there could be people in the room that have issues. And if that's the case, if you're one of those individuals, there is help for you, because I've seen people go down the wrong road before, and it's not pretty. So, but there's a lot of learning opportunities when it comes to games of chance. So I can't not do it, just instructionally, but it's definitely worth at least mentioning that you should be mindful of yourself and those you love, because it is dangerous. All right. So Kentucky Derby. Suppose the payoff odds for a horse to win the Kentucky Derby is 14-1. What would be the payout for a $500 wager? Right. So payoff odds is the net profit divided by the wager. Right, and it always depends on whether or not you get your wager back. In this case, they don't really clarify whether you get your wager back. So we're gonna make this a class rule. Assume you get your wager back unless told otherwise. The bet. The amount of money you bet. Good question. Because in most games of chance, you get your wager back, you get your bet back, but there are enough where it's not the case that you could look at it and say, well, I'd have to make an adjustment in those circumstances. So the payoff in this case is going to be, so the profit, let me just do that off on the side here, profit is going to be 14 times the 500, which is 7,000. I don't even know what that was. Some kind of glitch. All right. We're getting our wager back, so we're not losing the $500 that we put up. All right. If we did not get our wager back, we'd have to subtract that $500 off of the $7,000. We'd only be getting $6,500 back. All right. So the payoff odds would be 7,000 divided by 500, which actually ends up being the same thing as the payoff odds. All right. So they gave us that. But the payoff or the profit would be $7,000. That's what they're asking us for. All right. So you just have to understand that it could be a case where you have to subtract off the initial bet, but not necessarily the case in all situations. Lotteries, sometimes they don't give you your wager back, or at least in the way that you would expect. So you win the lottery. Like, I'm not talking about the big boy, like $47 million. If you win $47 million, the reason why you didn't get your wager back, your $1 wager back, is because you didn't ask for it. Because you just won $47 million. You weren't thinking about the $1 that you bet. Right? I'm thinking about like the little lotteries. Big lottery, but where you won a little prize. In most of those cases, you get the prize, maybe like a couple $100, but then you also get a free ticket. Right? That free ticket is you getting your wager back. So it's valued at the $1, but it's not the way that you would expect it. They're not just giving you $1; they're giving you an opportunity to spend more money, right? So that's a little bit of a different story. But as long as they give you the same value back, that's fine. In casino games, you put your chips on the table. So you're playing roulette or craps or something like that. You put $500 down on the table. If you win, they only add to that $500 that you put down, and then you take that money back. All right. So you're getting everything that you earned in your winnings, but you're also getting to keep that $500 that you bet. The amount that you risked, you still get that back. All right. So that's a little bit more obvious, I think, because otherwise, I mean, actually, maybe it's not obvious, because if you haven't been at a casino, you wouldn't necessarily know how much of a pain it would be to count everybody's chips and be like, wait, so you won, all right, so I got to take 500 from you because that was your wager, and then now I got to give it back, so I'm basically giving you that $500 back, but 500 less than the total amount, it would be complicated. All right? And they're so quick. You know, it depends on where you go, but they're quick enough that if you're not watching, they could pull some shenanigans on you and you wouldn't even know. Right? Somebody was telling me that was that one in Monticello. I forget what the name of it is, but there's like a new casino, Resorts World. Like they have local folks working there who aren't really very well trained in operating a casino. So, like, they're doing the math, not like the way they would do it in Vegas or Atlantic City. Because those people in Atlantic City and Vegas, they're like, here's yours, here's yours, here's yours, and then they know everything. You know, like, I honestly think they know more math than I do. And then you go to the other places, like the smaller places, and they're like, okay, scary moment. I thought I lost all that. Just need to recover for a second here. 47 minutes of video would have been down in the tubes, but just by accidentally hitting a power button, that's like too easy to touch. Yeah, the smaller places, they're actually doing the math on the fly. So I've heard stories about people getting told that they lost when they really won, or getting the wrong payouts, or going the other way, realizing that the person didn't know what they were doing, and when they actually lost, they would tell the person, no, I won. You're supposed to give me 30 times my wager. So start counting there, pal. You know, like that's pretty rough stuff. So definitely an industry to be mindful of, but it's all probability. And so this is the sample space information. Yeah, slots are easy. You just put your money in, you pull the thing. It's like, you know, it's rigged to some extent, but you just hope that all the bad luck is used up before you get there. Like, save some good luck for you, and then you go from there. I've heard enough stories about people who go to the casinos and they have their fun weekend, and on their way out, they're like, all right, we just go to the $100 slot. They put it in, pull, and then it's like, oh, the whole vacation's paid for. So it happens. It's just never happened to me. I had a moment where a valet was very rude to me. I was retrieving my car, and I did not tip him. And he's like, thanks a lot, man, no tip. I was like, dude, I just got cleaned out in the whole casino. Like, I have no money. I was really, really upset. I was getting into it with him. I'm like, who do you think you are? First off, it's not required. Second off, I have no money. I just blew it all in there. So get the hell away from me, you know? So that's, yeah, it's definitely an industry. You got to be careful. All right, but coins you're familiar with. Maybe not the array of 2 coins, 3 coins, and even more than that, but just a single coin and what it looks like on either side. A die. I unwrapped it. Well, I didn't do this, but I found a picture online of it being unwrapped so that you could see what the different sides would look like, and then a couple of dice paired together, and all the different outcomes that go along with that. and then the deck of cards, just in its full glory. So just to kind of familiarize yourself with it. It doesn't come out as clearly on your papers because it's not in color. But if you're not really familiar with a deck of cards, you may want to make a note of which ones are red and which ones are black. But if that's not something that's a problem for you, then you should be okay. Then you have the prime numbers. Definition of prime numbers: any number greater than 1. That is divisible by only 1 in itself. It's pretty common. I almost hit it again. Pretty common idea that's used in probability is to say, well, what's the probability of getting a prime number when you select a card from a deck or when you roll a die or something like that. So it's just worth having a handle on. But sometimes what we want to know is not so much what the total number of outcomes would be in a set. Sometimes we just want to know how many there would be in a total sample space. Like I don't need to list them all out like we would with the dice. If you're looking at the dice here, there's 36 possible outcomes. And that's a lot. If I threw in another die, so if I'm rolling 3 dice, there would be 216 outcomes. I wouldn't want to have to list them all out in order to know that there's actually 216 of them. So what I want to do is take some time and show you how you could determine how many elements there are that make up a sample space. And again, a sample space is really a listing, and I wrote this a couple pages ago for you, but it's a term that you need to know. So if you think writing it down a second time would be helpful, then go for it. So sample space is a list of all possible outcomes. So all possible in an experiment. In an asparagus? No, in an experiment. But again, here we're not looking to determine what they are, just how many there are. So I'm going to make a little table. One flip yields 2 outcomes. So I'm going to make a list here that says flip and outcomes. So one flip gives 2 outcomes. 2 gives 4 outcomes. 3 gives 8 outcomes. So the question is there a pattern? Now, I go through this all the time. It's like, is there a pattern? You could say yes or no, but you're not going to really learn from that. Like, yes, cool, but if you don't discover what that pattern is, it's not going to get you anywhere. Right? So let's investigate further. They didn't ask me this, but if there were 4 flips of a coin, how many outcomes would we be looking at? 16. Because it seems like we're doing what? Multiplying by 2. All right? So if I had 5, there would be 32. But what I want to do is figure out how I can get from the number of flips to the number of outcomes.
Question. So if we multiply 4 times 2, that would give us an 8. Then 8 times 2 will give us an 16.
Yeah. Yeah, so you're just doubling every step of the way. But now if I want to know, like if I had any number of trials, any number of flips, so n. But again, we want to generalize.
Did you mean to draw those three dots?
I did. I intended to. I don't intend for one of them to be spazzing out like that, but they should be there. So you want to think about how we could get from 1 to the 2, from 2 to the 4, from 3 to the 8, from 4 to the 16, from 5 to the 20, 5 to the 32. Now this little piggy needs to go home. So we end up with what is a power relationship, or exponential relationship, actually. So what's happening here is we're taking 2 and raising it to the first power to get that first number. The second number is actually 2 to the second power. The third one is 2 to the third power. Then we have 2 to the fourth power. Then 2 to the fifth power. All right, so the common thread here is that we have a base of 2, and the power just represents the number of flips. So if I have n flips, what's my power going to be? N, yeah. It's just whatever the number of flips would be. All right, so do you have to actually write it like that to understand the concept? No. Like, because if I had, once you've developed a trend, 2 to the first, 2 to the second, 2 to the third, and so on, if I had 16 trials, it would be 2 to the 16th. So, like if the 2 to the nth doesn't make too much sense to you, then write it in real terms. Write it in a way that you would understand. Like, and down here we're going to talk about a general formula, but I can kind of steal my own thunder. It seems like it is the number of outcomes for one trial and it's going to be raised to the number of trials.
So that's the answer to the question.
For the general formula one. Because we'll talk about dice in a sec, but this is the real person way of explaining what 2 to the nth means. Because 2 to the nth is a very mathematical way of representing it. But if you just think, all right, if I were to flip the coin once, how many outcomes would I have? 2. But I want to flip the coin 20 times, so 2 to the 20th. All right, so however many times you're doing that activity is what you would want. All right. So we can actually kind of go back and verify that for dice. All right, so we're looking at rolling a die, one roll gives us 6 outcomes. Let me just move that one over a smidge. Two gives us 36. All right. Determine the number of values in the sample space for 3 rolls of a fair die, 3 rolls of a die, but we're going to assume that it's kind of weird. I'll say die, and then sometimes I'll say fair die, or I'll say a coin, and sometimes I'll say a fair coin. I mean them interchangeably, because what an unfair die would be, or an unfair coin would be one of the ones that are loaded. So an unfair coin, for example, would be a coin that's got heads on both sides. In that case, what's the probability of getting tails? 0. Probability of getting heads? 1. An unfair die would be something, a die that's maybe heavier on one side, so that it allows certain outcomes to occur more frequently. Those we never assume are happening unless a problem explicitly states that. All right, so if I say coin I mean fair coin. If I say die, I mean fair die unless I give you the parameters of how it's unfair in the problem. All right. So in this case, it seems like we're multiplying by 6, just like in the last one we were multiplying by 2. But we could also look at this as 6 to the first, 6 to the second. And so the next one would be 6 to the third, which if you pop that in the calculator is going to be 216. All right. So then if I wanted to do any number of trials, like n trials, it would be 6 to the nth power. All right, because the number of outcomes for one roll of a die, 6 outcomes. If I roll the die 30 times, 6 to the 30th power.